Shall we start? So we are going to have a quiz 6 today. So we will discuss these exercises later. Okay? So we'll be studying the derivatives of various functions. And the one we started out was the polynomials, especially the power of x. X to the n, then the derivative. Okay, derivative came from the slope of the tangent line, right? Do you remember? So the x to the n, if you take a derivative, you get n times x to the n minus 1. Wherever or whenever n is an integer. But we expanded, or say, we studied a little bit, and especially for the case when a is a real number, we used the logarithmic functions to, say, take the derivative of x to the a. And a could be any real number, okay? But in this case, a has to be a positive number, okay? But in that case, using the logarithmic function, please look at the formula here. X is equal to the e to the y. That is if and only if by definition of the logarithmic function, y was equal to log of x, okay? When we delete the base, then we just assume that the base is e, which is a Napier's constant, which is a constant in between 2 and 3, right? And that's a very special number. That's a special number we like in mathematics. And so x is equal to e to the log x. So any x can be written as a power of e using a logarithmic function, okay? So if x to the a, if you want to take a derivative of x, the power of x, we just write this x as a power of e because we know the derivative of x to the e to the x. So using this formula, e to the a times log of x, and take a derivative. Then say a part is a constant, log of x is a complicated function, but we know by the chain rule, okay, chain rule, considering this part, e to the power part is so-called h of x, the inner function, okay, inside function inside. So using the derivative, firstly, just assuming this e to something, and take a derivative, you get e to something part, and then take a derivative of a times log of x. Just multiply that part. A is just a constant, so we keep a. And then the derivative of log of x was 1 over x, right? So we have a over x here. But e to the a log x, that was nothing but x to the a. So if you replace this part by x to the a, you get this part. But since you divide by x, that is the x to the minus first power, so this part can be simplified to get a times x to the a minus 1. But that is exactly the same as the formula we obtained for the case n is an integer, right? So we reached the conclusion that even if a is a real number, okay, for example, pi or e or 2.7 or something, okay, we can just apply the formula of the derivative x to the n, okay? But just a little thing we have to assume, that is x has to be positive, okay? Because if x is negative, for example, negative number to the square root, 1/2 power, then we have the complex number arises. So the other one, e to the x, which is already used, the derivative of e to the x, there's a constant, the power of a constant e, okay? So it's something like 2 to n, okay? 2 to n, n varies, and the 2 is replaced by a constant, another constant e, and the n part is replaced by x. So this is something like the power of 2, okay? So e to the x function, if you take a derivative, then the derivative doesn't change. You have e to the x, okay? So that's a special property of this special function. Okay? But you can also mimic the proof above to calculate the power of a as well. For example, a can be replaced by 2, so 2 to the x, that type of function is also differentiable and can be found a derivative in this way. But it's a little bit complicated and I will not touch it. But if you're interested in, please follow this line. Okay? So another one is log of x. If you take a derivative, you get 1 over x. Okay? To summarize, we discussed 3 types of functions. Okay? The first one is a power of x. Okay? The other one is e to the x. And then the third one is log x. Okay? You don't have to worry about anything else. Okay? Just 3 types of functions. One of them is a power of x. If you take a derivative, then the power part comes down, and then the power part decreases by 1. And n times x to the n minus 1 appears. Okay? And even if n is a real number or a quotient or something, then the same formula can be applied. Okay? Especially when you have, okay, I think you will see it in the quiz today. Okay, so for example, if you have square root of x, okay, then this is nothing but x to the 1/2, right? So if you take a derivative, okay, left-hand side it looks different, but this is the power of x, right? Power of x, so if you take a derivative, then this 1/2 comes down, and this one comes, the power part becomes 1/2 minus 1, right? So 1/2 x to the minus 1. This is the derivative of square root of x. Okay, what is this? Okay, this is, since you have a negative power, so this has 1 over 2, and then 1 over x to the 1/2 power, right? But that is nothing but square root of x. So you have 1 over 2 square root of x. Okay, right? So let me repeat again. Okay, so when you start with square root of x, okay, just change into a power form, x to the 1/2. Okay, then take a derivative, 1/2 comes down, and then subtract 1 from the power part, and then you get this, and then you get 1/2 x to the minus 1/2. But whenever you have some negative power, then that can be understood as a reciprocal of the power, say positive power. So you get this. Okay, the half x to the 1/2, that is if you multiply the same one again, x to the 1/2 times x to the 1/2, you get x to the first power. That means x to the 1/2 is the square root of x. That's why we have this. Okay? Right? All right. Now, next we study the first derivative test and the second derivative test, okay? The essential part is number 2 and number 3, okay? So whenever you have the positive derivative, f prime of c is positive, then if you go back to the definition of the derivative at x is equal to c, we could find that the f of x is increasing at x is equal to c. F prime of c is negative, then f of x is decreasing at x is equal to c. Okay? But sometimes f prime of c is equal to 0. Okay? F prime of c is equal to 0, but say if x is less than c, then that is always positive. And if x is greater than c, again, f prime of c, f of prime of x is always positive. Then in that case, you can also conclude that f of x is increasing. Okay? So even if f prime of c is equal to 0, if f prime of x is positive near x is equal to c, okay, then f of x is increasing. Okay? The similar things we can say describe for the case the negative. F prime of c is negative, then f of x is decreasing at x is equal to 0. X is equal to c, and also even if f prime of c is equal to 0, f prime of x is negative near x is equal to c, then f of x is decreasing. Okay? And the last one, f prime of x is equal to 0 for all x, f of x is constant. We haven't discussed this yet, okay? But we are going to use it in the when we discuss integration, okay? So let me see. F prime of c is 0, okay? When f prime of c is equal to 0, then we cannot conclude that f prime of c is positive or something. But the f prime of c is equal to 0, by this condition, if you take a contrapositive, you can get that f prime of c is, say, if f prime of x is 0 for all the time, then you can take that it's not increasing or decreasing, and you can tell that that is a constant. Okay. For the rigorous argument, we have to understand the so-called mean value theorem, but we will not discuss it. Just assume that the fact that f prime of x is 0 for all x, then f of x is constant. Okay, or f of x is equal to a constant. Okay, and we also discussed the second derivative test. Okay, f prime of c is 0, then f double prime of c is negative, then f of c is a local maximum. Okay, do you remember that? Okay, and there are several explanations of this. Okay, but okay, f double prime of c is negative. So I just explained using the chart. And c is here. So let's take the first case. So at c is equal at c, f prime of c is equal to 0, and f double prime of c is negative. Okay. In this case, since f double prime, this is the derivative of f prime. Okay. If you have one more dash of, let's say, from f dash, then this is the derivative of f dash. That is the derivative of f. Okay. So in this case, if it's negative, then the one preceding function, that is the f prime, this is decreasing at c. Okay. So it's decreasing. Okay. So at c, it crosses 0, but decreasing, and then hits 0, and then decreasing and decreasing. Okay, so by that, we can tell the signature, that is a positive or negative, of f prime. Okay, so before that part, it has to be positive, and it has to be negative after that. Okay? So that means f is since f prime is the derivative of f, okay, if it's positive, we know that it's increasing. And after that, it's decreasing. So you get that. So at x is equal to c, it's going up and going down. So this is the peak of the hill. Okay, so this is local max. So by that, oops, wait a second. It's good to tell. Okay. It's negative, okay? If it's negative, it's local max. Local max. Okay? Okay, good to check. Alright? So if it's f prime of c is 0 and f double prime of c is negative, and double prime of c is negative, then it's decreasing minus here. And then that is decreasing, so positive and negative. So you have to, f of x is increasing and decreasing, and at x is equal to c, it gets a local max. Okay. So what happens if f prime of c is equal to 0 and f double prime of c is equal to 0? Okay. In that case, there are several ways to do it. I will explain the second way later. But the best way I just explained last time is to take 2 prime of f and the 4 prime of f and so on. That means the derivative of f double prime is 2 prime and so on. Okay, so let me just quickly show it. Okay, so if you have x here and x is equal to c is equal to here, then f F prime, F double prime, F triple prime, F false prime, or so. Okay? Okay? Suppose that F is equal to C, X is equal to C, it gets 0, and F double prime is 0, F triple prime is, say, 0, okay? And the F false prime is, say, positive, okay? Okay? Then what happens? I will give you 1 minute, and please think about it. Okay, think about it. So let's start. So this is the false prime of F. It's a derivative of triple prime of F. Okay, so it's positive, so it's increasing. Okay, it's increasing, and it hits 0 at x is equal to c. So before c, okay, you have to have minus and plus. Okay, and then you think about F double prime. That is increasing or say decreasing by the signature of the derivative of that function. Okay, so it's negative, so you get going down and going up. Right? But it hits 0 at x is equal to c. That means at x is equal to c, this F double prime gets the local minimum. Okay? You can also apply the second derivative test. F double prime, if you take double prime, then you get here, right? So it's, say, second derivative, say first derivative is 0, and second derivative is positive, so you have the second situation. So that is local min. This is a local min, right? Local min is 0, that means the signature is always positive. Right? Going down and hit 0, and then going up. So the signatures are always positive. Right? Then from that you can tell the signature of, say, whether the nature of F prime. Okay? Since F prime, if you take a derivative, it comes down to F double prime, and that is positive and positive. Okay? So that means F prime is increasing and increasing. Right? So increasing and hit 0, and after that increasing. So the signature is negative and positive. Okay? So that means what is that? Then that is decreasing and increasing. So this is a local min. Did you get the logic? Okay? Okay, some of you are shaking heads, so let me explain the last part again. Okay? So first, you get this condition. Okay? Oh, let me start from here. Okay? It's positive, so from that, what we can tell is it's increasing. Okay? It's increasing. That's why we determine this one. Okay? It's increasing, and we know the value of F triple prime at x is equal to c. That is 0. Okay? Increasing and get 0, and then after that the value has to increase again. So that means the value has to be positive after you pass x is equal to c, and before that it has to be negative, right? Because it hits 0, but that is increasing and hits 0. That means before that it has to be negative. So by this, you could tell the value of the derivative of this particular function. So by the value of the derivative, you can tell whether that is increasing or decreasing. So here, you can tell that it's decreasing and increasing. But at x is equal to c, it hits 0. That means decreasing, hits 0, and increasing. So the value has to be always positive around that point. Right? So you get this condition. Now, you can tell that the function before that has to be increasing and increasing. Then hit 0 in the middle, and it has to be negative before that and positive after. So you get decreasing and increasing. Right? All right. Now, let's think about the next one. Find x when f of x is equal to e to the minus x squared is x maximum. Okay? In this type of case, I don't know whether I have it. Oops. Okay, it's not the one, but let me open it. Okay, so in this case, we use chain rule. Okay, so the function, the target function is this function. Okay, so we just call it e to something. Okay, e to something. So we set something part as the inside function. So set h of x is equal to e to the minus x. Okay, then say g of y is equal to e to the y. Then we can understand f of x is equal to g of h of x. Because g of y is this and y is replaced by, today I make a lot of mistakes. Minus x squared. Okay, if you replace y part by minus x squared, you get e to the minus x squared. That is f of x, right? So by the chain rule, which is written down here in the slide, you can tell that the f prime of x is equal to g prime of h of x and h prime of x. Okay, in this case, you have to know, say, what g prime of y is and also h prime of x. Okay, so h prime of x, it's a power of x, so it's easy. So you get minus 2x. And g of y, g prime of y, you get e to the y, because the derivative of e to the y is always e to the y. Okay? So from here, you can tell that the g prime of y is e to the y, and that y part is replaced by h of x, so e to the minus x squared. This is exactly the same function we had before in the beginning. And then times h prime of x. Don't forget this part. Okay? So that is minus 2x. So you have minus 2x. Okay? So since you have minus here, it's better to write this order. Okay? Otherwise, you have to put the parentheses. Okay? Yeah, so you get this one. Okay? Then what can we get? The problem says that find x when f of x is equal to e to the minus x squared is maximum. Okay? That means it's we find out the local max first. Then we first find out the value x such that f prime of x is equal to 0. Okay? But in this case, e to something, it's some positive number on the power. Okay? It never gets 0. Okay? So this part never gets 0. So the only case this function gets 0 is equal to x is equal to 0. Okay? So by that, we can tell that this f of x can have a local extremum at x is equal to 0. Okay? Look at the first one. F of x has a local extrema at x is equal to c. Then f prime of c is equal to 0. So if it's a local maximum, local minimum or so, okay, it has to get 0. The derivative has to be equal to 0. Okay, so you get x is equal to 0 as a possibility. Okay, one way to go further is to find the second derivative. Okay, so this is the first derivative. Okay, and for the first derivative part, let me just review the first derivative again. Okay, so you started out with e to the minus x squared. So in this case, e to something. E to something, if you take a derivative again, you get e to something. And then this is the derivative of the something part. Okay? So you get this one. Okay? Now you have this function, and then you have to take a derivative. Okay? But in this case, you understand it's a product of two functions. Okay? Two functions. So if you take a derivative, then you get the derivative of the first part. Derivative of the first part minus 2x. If you take a derivative, you get minus 2. Okay, and then keep that function. And then keep the function minus 2x. And then derivative of the second part. It's complicated, but this is exactly equal to f of x. So we know the derivative already. That is minus 2x e to the minus x squared. Okay? So you get this. Right? So if you just correct this part, this is 4x squared, right? So 4x squared minus 2 e to the minus x squared. Okay, so from this you get f double prime of 0 is, say if you get 0 here, then this is 1, so you get minus 2, so this is negative. Maybe difficult to look at the last line. F double prime of 0 is negative, so f prime of x is f prime of 0 is equal to 0, and f double prime is negative. So using this one, okay. So you can first part of the second derivative test, you can tell that that's a local maximum, okay, and that is the only local maximum we have. So it has to be the maximum value, okay, the largest value. Okay, so you have this, and you get this type of result. Okay, so from this, you can tell that this special function has a local maximum at x is equal to 0, and it doesn't have any other local extrema. Okay. And let's look at this function closely. Then this function has this type of shape. Okay? Some of you may be able to recognize this function. Okay? This is so-called a bell curve. Okay? There are many types of bells. Okay? But in mathematics or statistics, if we say it's a bell curve, then it represents this type of curve. Okay? Then at x is equal to 0, it gets a peak, and then going down both sides. Okay? And we found that f double prime of x is that one. Okay? And then from that you can tell when f double prime of x is equal to 0. Okay? Because e to the minus x squared part is positive, okay, always. So that is equal to 0 only when 2x squared minus 2 is equal to 0, right? When was it? 2 cancelled out, you get 4, sorry. Okay, so from this, you get 2x squared is equal to 1 over 2, right? So x is equal to plus or minus 1 over square root of 2. Okay? So at negative 1 over square root of 2 and the positive 1 square root of 2, it gets 0. Okay? What is the meaning of the double prime? Okay? Okay, I cannot just explain the geometrical meaning of it closely, but that is the case, that is a point when the rate of changes at some point. Okay, so derivative is the rate of change, right? So in this case, always positive in this area, okay? But the rate of change is at minus square root 1 over square root of 2 and the 1 over square root of 2, okay? So until reaching this point, it say quickly grows, okay? But after that, the rate of change just decreases a little bit, okay? So that point is called the inflection point. So this point, minus 1 over square root of 2 and 1 over square root of 2 is such a point, okay? The reason why I talk about this type of thing is that you will see it very often when you study statistics, okay? So please look at this function. Very complicated function, okay? Very complicated. But just look at the essential part, okay? This sigma is called the standard deviation, but it's anyhow, it's a constant, okay? And this pi is the, say, 3.14 and that number, okay? So anyhow, this part is a constant, okay? So this is a constant and e to some power, okay? So x is a variable and mu is also a mean or expectation. So you have, this is a constant. Sigma is a constant. So this is something like minus something square over constant, okay? So essentially, this is very similar to the function we just discussed, e to the minus x squared, okay? So, but it just shifted a little bit, okay? So, for example, in this case, the center is at x is equal to 0, okay? But for this function, center is at x is equal to mu. That is the average part, okay? So, it's a little bit different, but if you take a derivative carefully using the chain rule, then you get this. And this is equal to 0 at x is equal to mu, right? Because this part is very complicated, but this is positive, okay? So when you study statistics or some other field using applying calculus, okay? So some functions appear maybe very difficult, very complicated, but the essential part is not so difficult, okay? So look at the essential part. So this is e to something, and something part is x squared over 2. That is the essential part, okay? So in order for this to get 0, then you just look at this part because this is positive, okay? Then you can tell that f prime of x is equal to 0 only when x is equal to mu, right? So that means at x is equal to mu, that's the average, the curve gets the maximum. And what is the inflection point? Inflection point, if you solve this, then you can tell that is mu plus or minus sigma, okay? So sigma is called the standard deviation. So the average here, standard deviations, mu minus sigma and mu plus sigma, that is a point we are considering here as the inflection point, okay? So inflection point to inflection point, that is minus sigma to plus sigma. And the people, some of you who have already studied statistics a little, then you can tell that the area between minus sigma to sigma is 68% of the whole area, okay? So that means that sigma is the inflection point, okay? So that is a kind of the major part. And in the majority part, the 68% of the area, or the 68% of the whole thing in it. Okay? But if you take the 2 sigma or 3 sigma, I think you may have heard such a thing. Okay? Then you get more and more percentage of the whole area included in that region. Okay? And the first sigma, which we took, is the inflection point of this bell curve. Okay? Just take a note of it when you study statistics. Okay? Now, we have 5 more minutes. Let's think about this problem. F of x is something, okay? Right? And then we want to write it as a polynomial in x minus 2. Okay? We have done this before, okay? Using, for example, the synthetic division. Okay? But we have another way to find it. Okay? So that is, for example, to get a derivative of f of x. Okay? So in this case, you have a polynomial in x minus 2. Okay? So take a derivative, then you get, okay, 4 comes down, x minus 2 to the third power, plus 3a3 x minus 2 to the second power, plus 2a2 x minus 2 plus a1. Okay? In this case, by the chain rule, you have to multiply by the derivative of x minus 2. Okay? Because we assume this is a composite function, and the inside function is x minus 2. Okay? So assuming this is a polynomial in x minus 2, we took a derivative, just assuming that x minus 2 is just a chunk. Okay? Then we calculate this way. Then using the chain rule, we have to multiply x minus 2, derivative of x minus 2. But fortunately, if you take a derivative of x minus 2, that is 1. Right? Because if you take a derivative of x is 1. Right? 2 part disappears. So this is 1. So that's why you don't have to write this part. Okay? It's a chain rule. You have to multiply by the derivative of the inside function. But in this case, it's 1. So you don't have to write it. Okay? So if f prime of x is this, okay? Then can you tell f prime of 2? It's easy, right? If you plug 2 in, you get 0, 0, 0. Only case remaining is a1. Okay, so f prime of 2 is equal to a1, right? Then what is f double prime of x? Then again you have to take a derivative of this part. Okay, then let's try that. 12a4 x minus 2 to the second power plus 6a3 x minus 2 plus 2a2. Right? Right? So, what is f double prime of 2? Then 2a2 appears. Right? So, from this, you can get a2. a2 is f double prime of 2 over 2. Right? So, if you know the value of f double prime at 2, then you can determine a2. Okay? Right? You see that? Then what is f triple prime of x? Then that is 2 comes down, 24a4 x minus 2, plus 6a3, right? So if you take a value at 2, then you get 6a3. Okay? So from this, you get a3 is equal to f triple prime of 2 over 6. Okay? And if you understand this 6, okay, carefully in this formula, then you can tell that this 6 comes from this 3 times 2. So this is f triple prime of 2 over 3, which we call factorial. 3 times 2 times 1. Okay? So in this way, a4 also can be determined, and you can find other values as well. Okay, so for example, in this problem, we are supposed to find f of 2, f prime of 2, f double prime of 2, f triple prime of 2, these things, but these are calculated from a0, a1, a2 very easily. Okay, so if you look at this problem, exercise 4.7, okay, so we calculated by synthetic division. Okay, so but we also can say find these values, these coefficients, by taking derivatives. Okay? I don't have time to explain them, but this is another way you can find the coefficient of it. The reason why I explain this is that in the polynomial case, we can use synthetic division. But in other case, we cannot have the synthetic division. Okay? So, okay, in that case, we also think about a similar function like this. And the g of x can be written in this way. It's a little bit complicated, but this type of expression, okay, can give a value, approximate the value near x is equal to 2. In a similar way, you can express the function in this way to give us, say, approximation of the value of the function. Okay, I will say come back to this one sometime later in the next section. Okay, so that is called the Taylor series and Maclaurin series. Okay, and for example, sine of x can be written in this way, and you have a calculator. If you have a calculator or even the smartphone, you can get a value of sine of x. Okay, but inside the calculator, what they are doing is just multiplication and addition. They don't have sine x. Why can we find the value? Because they are using this formula. Okay, so everything computer can do is just addition and multiplication. Okay, so even by that, you can find the approximate value of sine of x or exponential of x. Okay, so in that way, we can find the value of a complicated function. But that is, they are using, the computer is using these polynomials or approximation by polynomials. Okay, let's stop here. Okay, let me just go back to the announcement again here. Okay, so quiz 6, quiz 5, okay, is available, but also the short paper is now available in the Moodle. Okay, so if you go to the Moodle, you can read the, let's say, short paper of others. As I mentioned, those are available now on the website, okay, Moodle. And I will return it on Wednesday, I think, okay, with quiz 6, hopefully.